Hello, in this lecture we will find the radius of the small circle. In the drawing we have two circles. Those two circles have an internal lunge between them at this point. They touch each other internally at this point. Let's call this point point N. Again, point N is the point of lunge between those two circles, and we know that AC equals to 9 units. AC equals to 9 units. BD equals to 4 units. And this is a right angle, and also this angle equals to 90 degrees. Actually, this is also a right angle because we have here a straight line, and along a straight line the sum of the angles equals to 180 degrees, and if this angle is 90 degrees, then this angle must complete the sum of the angles along this straight line to 180 degrees, so it must be also 90 degrees. And for the same reason, this angle is also 90 degrees. It is a right angle, and the small circle has 3 tangents. This is the first tangent. This tangent is tangent to the circle at this point. Let's call this point point S. Again, point S is the point of contact between the tangent and the circle, and also we have here the second tangent. This tangent is tangent to the circle at this point. Let's call this point point M. Point M is the point of contact between the circle and its tangent, and we also have the third tangent to the circle. The tangent is tangent to the circle at this point. Let's call this point point Z. Point Z is the point of contact between the tangent and the circle, and let's define the center of the small circle as point Q. Again, point Q is the center of the small circle, and let's define point P as the center of the big circle. Again, point P is the center of the big circle, and so I will write it down that point Q is the center of the small circle, and point P is the center of the big circle. So I will read again the things that I wrote. Point P is the center of the small circle, and point P is the center of the big circle. In the next step, we will define the radius of the small circle as small r, and the radius of the big circle as capital R. Okay? So small r is the radius of the small circle, and capital R will be the radius of the big circle. So I will read again what I wrote. Small r is the radius of the small circle, and capital R is the radius of the big circle. And in the next step, we will draw three radiuses of the small circle from the center of the circle to the launch point. Okay, so this will be the first radius of the small circle from the center of the circle, that is to say from point Q until it touches the launch point at point S. So this is the radius of the circle, and we will draw the second radius of the circle from the center until it touches the circle at the launch point at point Z. So actually the radius touches the launch point, that is point Z. Okay, this will be the second radius, and then I will draw the third radius from the center of the circle until it touches the launch point, that is to say until it touches point M, that is the launch point between the circle and its tangent. Okay, so we have three radiuses that are drawn to the launch points of this circle. Actually, we have a rule number one. Rule number one states that a tangent to the circle is perpendicular to the radius drawn to the launch point. Okay, so I will read rule number one again. rule number 1 states that the tangent to the circle is perpendicular to the radius drawn to the launch point. Again, a tangent to the circle is perpendicular to the radius drawn to the launch point. Okay, so actually the meaning of rule number 1 is that if a radius of the circle is drawn to the launch point, that is to say here to point S, then the tangent will be perpendicular to that radius. Again, this radius actually even touches the launch point, point S. So therefore, the tangent is perpendicular to that radius. So whenever you draw a radius that is drawn to the launch point, that is to say to point S, then the tangent will be perpendicular to that radius. And also here we have radius small r that is drawn to the launch point. Actually it touches the launch point, that is to say point Z. So therefore, according to rule number 1, the tangent is perpendicular to that radius, that is to say this angle is a right angle. And also here the radius touches the launch point. Actually it is drawn to the launch point, therefore the tangent is perpendicular to the radius, therefore this angle is a right angle. And also the third radius is drawn to the launch point. Actually it touches the launch point, therefore the tangent is perpendicular to that radius. That is to say this is a right angle, and this angle also equals to 90 degrees. Okay, so again, a tangent to the circle is perpendicular to the radius drawn to the launch point. So actually these three radiuses are drawn to the launch point. The launch points of this circle are S, M, and Z, and those three radiuses actually touch the launch points. They are drawn to the launch points. Therefore, according to rule number 1, the tangents are perpendicular to those radiuses. Okay, this radius is drawn to the launch point, it touches the launch point, therefore this angle is a right angle because the tangent is perpendicular to the radius. Also this radius is drawn to the launch point, it touches the launch point, therefore the tangent is perpendicular to that radius, that is to say this angle is a right angle. And also the third radius is drawn to the launch point and it touches the launch point. For that reason, according to rule number 1, the tangent is perpendicular to that radius, that is to say this is a right angle, and also this angle equals to 90 degrees. Okay, so actually we will focus on quadrilateral QZMD. Okay, quadrilateral QZMD. Okay, we will focus on quadrilateral QZMD. this quadrilateral QZMD has 3 right angles, 1, 2, and 3. So the sum of 3 angles is 90 degrees times 3 is 270 degrees. The sum of its 3 angles equals to 90 degrees times 3 is 270 degrees. Okay, the sum of its 3 angles equals to 270 degrees, that is 90 degrees times 3 is 270 degrees, and we have a rule number 2. Rule number 2 states that the sum of the angles, the sum of the angles of a quadrilateral equals to 360 degrees. Okay, I will read rule number 2 again. Rule number 2 states that the sum of the angles of a quadrilateral equals to 260 degrees. So actually, according to rule number 2, the sum of the 4 angles of quadrilateral QZMD must be equal to 360 degrees. So the sum of the 3 angles, that is 270 degrees, plus the sum of the 4th angle, that I will call it, plus the size of the 4th angle, that I will call it y. Y is the size of the 4th angle. Y is the size of the 4th angle of quadrilateral QZMD. So 270 degrees plus the size of the 4th angle, that is y degrees, must be equal to 360 degrees. So I'll read again the things that I wrote. According to rule number 2, first of all, we defined y as the size of the 4th angle of quadrilateral QZMD. And we know, according to rule number 2, that the sum of the quadrilateral, the sum of the angles of quadrilateral QZMD must equal to 360 degrees. So the sum of its three angles is 270 degrees, plus the size of the fourth angle in total must be equal to 360 degrees according to rule number 2. Okay, this must be according to rule number 2, that the sum of the four angles of a quadrilateral must be equal to 360 degrees. Okay, so from this equality we will subtract 270 degrees and we will get that angle Y equals to 360 degrees minus 270 degrees, it equals to 90 degrees. So the fourth angle is also a right angle, it equals to 90 degrees, it is a right angle. So actually quadrilateral QZMD has four right angles. Okay, this quadrilateral QZMD is four right angles, and we have rule number 3. According to rule number 3, any quadrilateral that has four right angles is a rectangle. I will read rule number 3 again. Rule number 3 states that any quadrilateral that has four right angles is a rectangle. Okay, it is a rectangle. So according to rule number 3, quadrilateral QZMD is a rectangle. Okay, according to rule number 3, quadrilateral QZMD is a rectangle. According to rule number 3. So, and we have also rule number 4 that states that according to rule number 4, the opposite sides of a rectangle are equal to each other. So I will read rule number 4 again. Rule number 4 states that the opposite sides of a rectangle are equal to each other. So from rule number 4 we can deduce that QZ equals to MD. QZ, side QZ of rectangle QZMD is opposite to MD, so QZ equals to MD according to rule number 4. Okay, QZ equals to MD according to rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay, side QZ equals to side MD in rectangle QZMD. Okay, QZ equals to MD, but QZ is the radius of the small circle, so QZ equals to small r because it is the radius of the small circle. Okay, QZ is the radius of the small circle, that is to say it equals to small r, and from this equality we can deduce that MD equals to r. Okay, MD equals to r. MD equals to small r. MD equals to small r, so actually this is side MD, and according to rule number 4 that the opposite sides of a rectangle are equal to each other, MD equals to small r. And actually we will repeat on the same process on quadrilateral SQCM. On quadrilateral, this quadrilateral SQCM, we have three right angles. Therefore, according to rule number 2 that states that the sum of the angles in a quadrilateral are equal to 360 degrees, the fourth angle must be equal also to 90 degrees. So quadrilateral QZMD has 4 right angles, and according to rule number 3 that states that if a quadrilateral has 4 right angles, then it is a rectangle. Quadrilateral QZCM is a rectangle, and we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. That is to say, SQ equals to CM, because QSCM is a rectangle, so the opposite sides of a rectangle are equal to each other, so SQ equals to CM. But we know that SQ equals to small r, so therefore CM also will be equal to small r. Okay, so we concluded that Cm also equals to small r, and in the next step we will define Pm as x, that is to say Pm will be equal to x according to our definition. Pm equals to x. So what is the value of Cp? What is the value of Cp? Actually, Cp equals to Cm minus Pm. Very simple. Cp equals to Cm minus Pm. Okay? But we found out that Cm equals to small r and Pm equals to x according to our definition. So in total we got that Cp equals to small r minus x. Okay, so I write here that Cp equals to small r minus x. Okay, Cp, this line segment, equals to small r minus x. Okay, in the next step we will calculate the size of the radius of the big circle in two ways. Actually, we know that AB is the diameter of the big circle, therefore AB equals to 2 times the radius of the big circle, that is to say AB equals to 2 times capital R, and AB equals to AP plus PB. Okay, AB equals to AP plus PB. Okay, from the drawing we can see that AB equals to AP plus PB. Okay, AB equals to AP plus PB. But AP is the radius of the big circle, because P is the center, and PB is also the radius of the big circle. So AB equals to 2R equals to AP, that is capital R plus capital R. Okay, so AP equals to capital R and PB equals to capital R. So we will create two equations for the radius of the big circle. The first equation will be the equation that says that AP equals to capital R, because P is the center of the big circle. So the first equation will be that AP equals to capital R. Okay, AP equals to capital R. But what is the value of AP? AP equals to AC plus CP. Again, AP equals to AC plus CP. Very simple. AP equals to AC plus CP. But we know that AC equals to 9 units, it is given us in the question, and CP equals to small r minus x. We found out that Cp equals to small r minus 6. So in total, AP that equals to R, it is actually equals to 9 plus small r minus x. Okay, so in total, AP that equals to capital R equals to 9 plus small r minus x. That is the value of capital R, so I didn't write here AP because it equals to R. Okay, AP that equals to R equals to 9 plus small r minus x. But we have also the second equation that states that PB also equals to capital R. Okay, according to the second equality, PB also is the radius of the big circle, it equals to capital R. Okay, but what is the size of PB? From the drawing we can see that PB equals to PM plus MD plus DB. Again, PB equals to PM plus MD plus DB. So I will write it down that PB equals to PM plus MD plus DB. Okay, PB equals to PM plus MD plus DB. Okay, so and PM equals to, okay, that is the equation that PB that equals to R to capital R equals to PM plus MD plus DB. But what is the value of PM? PM equals to X according to our definition, and MD is the radius of the small circle, and DB equals to 4 because it is given us in the question. So in total we got that PB that equals to capital R equals to X plus R plus 4. Okay, so we can write down that PB equals to capital R, so I write only capital R, the radius of the big circle, equals to X plus small r plus 4. Okay, that is our second equation. So we actually have two expressions for the radius of the big circle. From one side it equals to X plus R plus small r plus 4, and from the other side the radius of the big circle equals to 9 plus small r minus x. So because we are talking on the same radius, we have two different expressions from the same radius, so we can create equation number 3 that states that the radius according to the first expression and the equation equals to the radius according to the second equation and the expression, or capital R equals to capital R. Okay, so actually our third equation is that our third equation states that capital R according to the first expression is equals to capital R according to the second expression. Okay, so I write down the first equation for, I substitute capital R here for by the first expression, and I will substitute this capital R by the second expression and equation. Okay, and we will get that again, expression number 3 states that capital R according to the first equation equals to capital R according to the second equation. Okay, because we are talking on the same radius. So here we have small I on this side of the equation, and we have small r on the other side of the equation, so we can cancel r, and what is left after we cancel r is so we got that after we cancel r, what is left is 9 minus x equals to x plus 4. Here we will subtract 4 from this equality, and we will get that five minus x equals to x. So after we subtracted 4 from equation number 3, this equation, we got that 5 minus x equals to x. Here we will add x to this equality, and we will get that 5 equals to 2 times x. So after we add x to this equality, we got that 5 equals to 2x. Here we will divide this equality by 2 in order to get the value of x. Okay, so we will get that x equals to 5 over 2 is 2.5 units. Okay, we found out the value of x. X equals to 2.5 units. So after we know the value of x, we can substitute x in the first equation by 2.5 units. So we will do it now. We have expression number 1 that states that the capital R equals to 9 plus small r minus x. Okay, that is equation number 1 for the radius of the big circle. So here we have x, so we can substitute x by 2.5 units. And we will get that capital R equals to 9 plus r minus x, and instead of x we write down 2.5 units. So we got that r equals to 9 plus r minus 2.5. 9 minus 2.5 is 6.5. So in total we got that the value of the capital R equals to 6.5 plus small r. Okay, we found that the size of the radius of the big circle equals to 6.5 plus small r, that is to say the radius of the big circle is bigger by 6.5 units than the radius of the small circle. Okay, so, and we also know that x equals to 2.5 units. So in the next step I will present a rule, new rule, rule number 5, and we will implement rule number 5 in our two circles. So rule number 5 states if two circles have internal length between them, that is to say, if two circles touch each other internally at any point, they have point of contact internally, then the distance between their centers is equal to the difference between the lengths of their radiuses. So I will read rule number 5 again. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Between the lengths of their radiuses. So I will read rule number 5 again. According to rule number 5, if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so if two circles touch each other internally, or then the distance between their centers is equal to the difference between their radiuses. Okay, so actually we can implement rule number 5 in our circles, because we have here two circles that have internal length between them at this point, at point N. They touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, the center of the small circle is at point Q and the center of the big circle is at point P. So the distance between their circles is PQ. Okay, PQ, according to rule number 5, this distance PQ equals to the difference between the lengths of their radiuses. The length of the big radius is capital R, and the length of the small radius is small r. So, and the difference between those radiuses is capital R minus small r. So the distance between their centers, that is to say QP, equals to capital R minus small r. Okay, so I will write it down that according to equation number 4, QP, that is the distance between the centers of those two circles, equals to the difference between their radiuses. That is to say capital R minus small r. Okay, so actually equation number 4 is the implementation of rule number 5 in our two circles, because we have here two circles that touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, that is to say QP, equals to the capital R minus small r, the difference between the radiuses. So QP equals to capital R minus small r. Okay. Here we can add capital R to, we can add small r to this equality, and we'll get that capital R equals to QP plus small r. Okay, we got this equality that says that capital R equals to QP plus small r. Okay, but we have already found out the question number 1, that capital R equals to 6.5 plus small r. Okay, so actually we have two expressions for the same radius. So Of course, they are equal to each other, so we can create equation number 4 that states that capital R equals to capital R, or capital R according to equation number 1 equals to capital R according to equation number 4. It is the same radius. Okay, so we write here that capital R according to equation number 1, that is 6.5 plus small r, equals to capital R according to equation number 4, that is QP plus small r. Okay, again, equation number 5 is the statements that capital R according to equation number 1 equals to the same capital R according to equation number 4. Okay, so here we have small r in this side of the equation, and we have small r on the other side of the equation, so we can cancel r. After we cancel r, we will get that QP equals to 6.5 units. Actually, QP is the distance between the centers of these two circles, and it equals to 6.5 units, and we have already found out that x equals to 2.5 units. Okay, QP equals to 6.5 units and x equals to 2.5 units. So in the next step we will connect together points Q and P by a straight line. So actually we have here triangle QMP, triangle QMP is a right triangle because angle QMP is a right angle. Okay, so I will write it down that triangle QMP, that is right triangle. Actually, you can implement the Pythagorean theorem in the right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse in the right triangle QMP equals to QP square equals to the sum of the squares of the perpendiculars equals to PM square plus QM square. This is according to the Pythagorean theorem. So according to the Pythagorean theorem, QP square equals to PM square plus QM square. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. But what is the value of QP? We have already found out that QP equals to 6.5 units. So QP equals to 6.5 units, and QP square is 6.5 square equals to PM square. What is PM? PM equals to X according to our definition, and we have already found out that X equals to 2.5 units, so PM square will be equal to 2.5 square plus QM square. QM equals to small r. It is actually the radius of the small circle, so QM square is r square. So in total we got that 6.5 square equals to 2.5 square plus small r square. 6.5 square is 42.25, and 2.5 square is 6.25. So I write it down. So we got that 42.25 equals to 6.25 plus small r square. Here we can subtract 6.25 from this equality. So 42.25 minus 6.25 is 36. 36 equals to r square. Here we will take a root out of this equality, and we will get that the root of r equals to small r equals to the root of 36. The root of 36 is 6. So we got that the radius of the small circle equals to 6 units. Again, the radius of this small circle equals to 6 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. We know that the two circles have internal length between them at point N. That is to say, they touch each other internally at point N, and we know that this small circle has 3 tangents. This is the first one, this is the second one, and this tangent is the third one. And those 3 tangents have 3 launch points. The launch point of this tangent with the circle is at point S. The launch point of this circle with this tangent is at point Z, and the launch point between the circle and this tangent is at point M. And we also know that AB is the diameter of the big circle, BD equals to 4 units, AC equals to 9 units. This is a right angle, this is also a right angle. And we want to find out the radius of the small circle. Okay, so we defined the small r as the radius of the small circle and capital R as the radius of the big circle. And we also defined Q, point Q is the center of the small circle, and point P is the center of the big circle. Then we drew 3 radiuses of the small circle. Those 3 radiuses exit from the center of the circle, and hence they touch the launch points of this circle. Actually, they are drawn to the launch point. Okay, and actually we have rule number 1 that states that a tangent to the circle is perpendicular to the radius drawn to the launch point. Okay, so if you have a tangent, if you have a radius that is drawn to the launch point, then this radius is perpendicular to its tangent, or the tangent is perpendicular to that radius. It is exactly the same thing to say. So here we have this tangent to the circle, and the launch point is point S between the tangent and the circle, and this radius is drawn to the launch point. Therefore, according to rule number 1, this tangent is perpendicular to that radius. That is to say, this angle is a right angle, and the same thing we have here. We have radius that is drawn to the launch point, that is to say to point Z. Therefore, according to rule number 1, this tangent is perpendicular to that radius that is drawn to the launch point. Actually, this radius touches the launch point, point Z. Therefore, according to rule number 1, this tangent is perpendicular to that radius, that is to say this angle is 90 degrees. And also we have the third radius that is actually drawn to the launch point, to point M. Okay, so whenever you have radius that is drawn to the launch point, then the tangent will be perpendicular to that radius, or the radius will be perpendicular to its tangent. That is to say, this angle is 90 degrees, and also this angle is 90 degrees. Okay, again, rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to the launch point, and those 3 radiuses, all of them are drawn to the launch points. Therefore, according to rule number 1, they are perpendicular to their tangent. That is to say, this is a right angle, this is also a right angle, and this is also a right angle. Okay, so actually we will focus on quadrilateral QZMD. This quadrilateral has 3 right angles, 1, 2, and 3. And the sum of those 3 right angles equals to 90 degrees times 3 is 270 degrees. And we have rule number 2 that states that the sum of the angles of a quadrilateral equals to 360 degrees. Therefore, the sum of the angles in quadrilateral QZMD must be equal to 360 degrees. So we have already 3 angles that the sum of them is 270 degrees, plus the 4th angle. The sum of those 4 angles must be equal to 360 degrees, according to rule number 2. Again, the sum of those 3 angles plus the size of the 4th angle, that is y, must be equal to 360 degrees, according to rule number 2. So here we subtracted 270 degrees from this equality, and we got that the size of the 4th angle, that is y equals to 90 degrees. So actually quadrilateral QZMD has 4 right angles because this angle is also a right angle according to rule number 2, and we have rule number 3 that states that any quadrilateral that has 4 right angles is a rectangle, or if a quadrilateral has 4 right angles, then it is a rectangle. So quadrilateral QZMD has 4 right angles, and therefore according to rule number 3 it is a rectangle. Okay, and quadrilateral QZMD is a rectangle according to rule number 3. And we also have rule number 4 that states that the opposite sides of a rectangle are equal to each other. Okay? Quadrilateral QZMD is a rectangle according to rule number 3, and according to rule number 4, the opposite sides of this rectangle are equal to each other, so QZ equals to MD. According to rule number 4, the opposite sides of the rectangle are equal to each other, so QZ equals to MD. QZ equals to MD. But we know that QZ equals to small r. QZ is the radius of the small circle. Okay, QZ equals to r. So from this equality we can derive that MD equals to r, or MD is the radius equals to the radius of the small circle. And we repeated on the same process on quadrilateral QSMC. This quadrilateral has 3 right angles. So according to rule number 2, that the sum of the angles in any quadrilateral equals to 360 degrees, then the fourth angle must be also equal to 90 degrees. This is actually a right angle according to rule number 2, and according to rule number 3, that if a quadrilateral has 4 right angles, then it is a triangle. So quadrilateral SQCM is a rectangle. Rule number 3 states that if a quadrilateral has 4 right angles, then it is a rectangle, and this quadrilateral SQCM has 4 right angles, then therefore it is a rectangle. And we have rule number 4 that states that the opposite sides of a rectangle are equal to each other. That is to say, QS equals to MC or CM, but we know that QS equals to small r, therefore CM that equals to QS also must be equal to small r, so CM also equals to small r. Okay, then we defined PM as x, so CP will be equal to CM minus MP, that is to say CP equals to CM that is r minus PM that is x, so CP equals to small r minus x. Okay, and we know that AB is the diameter of the big circle, that is to say it equals to 2 times r, and AB equals to AP plus PB, and AP equals to the radius of the big circle because P is the center of the circle, and PB is also the radius of the big circle. Okay, so we created 2 equations for the radius of the big circle. The first equation states that AP equals to the radius of the big circle, so AP will be equal to AC plus CP, or we got that AP, that is the radius of the big circle, equals to 9 plus r minus x, because AC is 9 and CP is r minus x. So capital R equals to 9 plus small r minus x. And we also know that PV equals to the radius of the big circle, but PV equals to PM plus MD plus BD. So PV will be equal to PM, that is x, plus MP, that is small r, plus BD, that is 4. So we got that capital R equals to x plus small r plus 4, and we know that also that capital R equals to 9 plus small r minus x. So we have two expressions for the same radius, equation number 1 and equation number 2. So because those expressions are expressions for the same radius, of course they are equal to each other. So we got equation number 3 that states that the radius according to equation number 1 equals to the radius according to equation number 2. That is equation number 3, and from equation number 3 we got that x equals to 2.5 units. And we have equation number 1 that states that capital R equals to 9 plus small r minus x. And we have already got the value of x that is equals to 2.5 units. So we can substitute x in equation number 1 by 2.5 units. And we got that the radius of the big circle according to equation number 1 equals to 6.5 plus small r, that is the radius of the small circle. Okay, then we presented rule number 5, and we implemented then rule number 5 in our circles. Rule number 5 states that if two circles have internal length between them, then the distance between their centers is equal to the difference between the lengths of their radiuses. Okay, so if two circles touch each other internally, then the distance between their circles are equals to the radius of the big circle minus the radius of the small circle. Okay, so we actually implemented rule number 5 in our circles, because we have in our circles internal length between them. They touch each other internally at point N. Therefore, according to rule number 5, the distance between their centers, that is to say QP, will be equal to the radius of the big circle, that is capital R, minus the radius of the small circle, that is small r, or in other words, QP will be equal to capital R minus small r. From equation number 4, we got that capital R equals to QP plus R, but according to equation number 1, capital R equals to 6.5 plus small r. So we have two expressions for the same radius. So of course we can compare equation number 1 to equation number 4, because both of them are expressions for the same radius. So we created the equation number 5 that states that the radius, the big radius, according to equation number 1, equals to the expressions of the big radius according to equation number 4. Okay, and from equation number 5 we got that QP equals to 6.5 units, and we have already know that x equals to 2.5 units. Okay, then we connected together points Q and P by a straight line, and we have triangle QMP that is a right triangle because of the fact that angle QMP is a right angle. So we can implement the Pythagorean theorem in the right triangle QMP. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say QP square equals to PM square plus MD square. And we know that QP equals to 6.5 units and PM that equals to x equals to 2.5 units. And the only missing variable here is QM, that is the radius of the small circle. So we put the data inside this equality and we got the radius of the small circle. We found out that the radius of the small circle equals to 6 units. Again, the radius of this small circle equals to 6 units, that is to say small r equals to 6 units. Okay, thank you very much.